Okay, let's have a little look at this real quick.
Just watched it a little bit.
So a problem like this is on the second 11.2 assignment, I think, second practice from chapter 11.
Oh, if we're leaving for the track meet, we will leave at 40.
When is
Thought
it?
it on-
I think we're either leaving 35 or 40.
I thought Taylor said that it was at 1:30.
1:30.
Well, you know,
I'm not going. I didn't sign up.
Well, I don't know. Why don't you go find out?
Okay.
better be early than late.
Yeah. Safety first.
Unless you just skip school.
Okay, so bike rider approaches a hill on a level road. I want to do this two ways. First way, so I'm going to just copy this thing. Okay, first way, let's just do this with the plain old work energy theorem, right? So we know that the net work equals the change in kinetic energy, right? Okay, so here's our picture. We've got a bike that's traveling along the level ground, right? So here's our bike. Traveling along the level ground with a speed of 16.4 meters per second. It encounters a hill, and it's going to coast up the hill, and it's going to end up at some height above the level ground, right? 11.2 meters, they tell us, right? Okay, so we want to know what fraction of the initial energy did the biker lose to friction as he coasted up the hill. Okay, so what's that going to look like? Our answer is going to look like the work done by friction, right? Everybody agree? Because that's the energy lost to friction. Okay. So the work due to friction, and let's just put it in absolute values, because we're just trying to find if it's negative, we'll make it positive. We just want an amount. How many joules did we lose to friction, right? Divided by the initial energy, right? Okay. Initially, when this bike rider is riding along, all the energy is what? It's all kinetic, isn't it, right? Because we're going to set the height. This is where we're going to set h equal to 0, right? If we're even going to use gravitational potential energy. We don't have to if we're just going to do it this way, right? But second way we're going to do it, we will, right? So then it's just going to be divided by the initial kinetic energy. That's what we're looking for as a decimal or a percentage or something, right? Okay, so how are we going to get that? So the net work means the work done by all the forces. So as the object is traveling up the hill, the bike is traveling up the hill, what forces are acting on it?
Gravity.
Okay, so gravity's acting on it. Gravity's acting in what direction? Down, okay. What else? Friction is acting in which direction? Okay, against, parallel to the surface, resisting its movement, right, slowing it down. And one other one? Normal force. Normal force is acting normal to or perpendicular to the road. So which of those forces are doing work? Gravity is, but not normal force, right? Because it's acting perpendicular to the motion, so it doesn't do any work, right? So then the net work is going to be the work due to gravity plus the work due to friction. Okay, so everybody agree so far?
Yeah.
Okay, so net work due to gravity plus work due to friction equals the change in kinetic energy. Okay, well, change in kinetic energy just means final kinetic energy minus initial kinetic energy. What's the final kinetic energy? Zero. It's coming to rest, right? So the change in kinetic energy is just 0 minus the initial kinetic energy, right? So isn't that just equal to then, that's just equal to negative, so 0 minus 1/2 m v naught squared, right? Everybody agree? Okay. So then if we want to do this, okay, so if we want to do, all right, we need to find the work due to friction, right? So the work due to friction is equal to the change in kinetic energy, so negative 1/2 m v naught squared minus the work due to gravity. What's the work due to gravity? We can calculate that, right? The work due to gravity, let's separate that part out. So we need to be able to put in a value for that. The work due to gravity is just the gravitational force times the displacement, vertical displacement, right? Because the lines of gravitational force are vertical. Everybody agree? Okay? So we don't care, it doesn't matter how steep this ramp is as far as gravity is concerned. Without any friction, these two ramps, like if I've got, let's say here's one ramp, takes off from there and it's real gradual, and one ramp takes off from here and it's real steep. If I had a bike that travels this path up the long ramp, or this path up the short ramp, it doesn't matter. They're going to have the same speed at that point, aren't they? Right? Because gravity is going to have done the same amount of work both times. All the work done by gravity depends on is how far did they move vertically, right? Okay, so going back to our picture here, this is the vertical distance that they traveled. It's 11.2 meters, right? So the work due to gravity then is just going to equal the gravitational force, which is just mg, right, the weight. Everybody agree? Okay, so mg times the height, which we know, I'm just going to call it h, but it's 11.2. We'll plug that in later, right? What about the sign? If the force is acting in the same direction as the displacement, that's positive work. But what if the force is acting against the direction of motion? That's negative work, right? And one way we can always reconcile that is that the angle is 180 degrees, right? So we got to put a negative sign out front. All right, so now we can plug that in up here. If I'm subtracting the work due to gravity, that's like adding, right? I'm subtracting a negative, so I'm adding mgh. So there's the work due to friction. Agreed? Okay. All right, so that's what I can put up there. The initial kinetic energy is just this.
Are you recording this?
I better be. I am. Yeah, good. I am recording this one. Yeah, no, I am recording. So everybody agrees that's the initial kinetic energy, right? 1/2 m times the initial speed squared. So now I can set this ratio up. I can simplify that ratio. I can write that ratio as work due to friction, right? So the answer is just going to equal negative mgh divided by the initial kinetic energy. That's 1/2 m v naught squared. And even though I don't know the mass of the bike, it doesn't matter, does it? Right? It doesn't matter because the masses are going to cancel. Okay? And so we end up with whatever that is. If we plug in numbers, this is a calculator issue, so we can just plug in some numbers here. Okay, so what are we going to get? We're going to get on the top. So we get the quantity. We get the quantity negative. Well, I'm just going to make it positive, right? We're going to make the top positive. So we can ignore the negative sign. We just want an amount. So G is 9.8 times, wasn't the height 11.2? Divided by the quantity 0.5. Whoops. Oh my gosh, are you kidding me?
Perfect.
Did I just do that? 9.8 times 11.2 divided by the quantity 0.5 times, what was the initial velocity? I forgot.
16.4.
16.4. 16.4 squared. Okay, and that gives us the answer. Oh, holy smokes. Did you bring it? Did you bring it, Sam? Oh, man. So we lost, so the amount of energy lost to friction represents about 82% of the initial kinetic energy, right? The initial energy. Okay? All right, so that's one way to do it. All right, here's the other way to do it.
Is this the easier way?
I think it is. I think it is.
So I don't need to learn this way.
Next week, you don't come to school.
Okay, so here's the other, does everybody, give me a 1 to 5 on that last one. 5 meaning, okay, I got it. 1 meaning, no clue.
3 or 4.
Meaning
Once I look at the video again, I'll say like 4 or 5.
Okay, okay. So we're within striking distance of that problem. All right.
Well,
Oh,
he is.
Okay.
I'm gonna say, 1.183.
1.183.
Yeah.
Okay. All right. So we'll need to go through one of those, maybe. Try one and then.
Yeah, no, it's-
Yeah.
I'm probably gonna come with
Kind of
that.
just matching my 100 time within the decimals.
I gotcha. Okay, gotcha. Okay, so now here's the other way. This is the more sophisticated way. We're gonna use the alternate version of the work energy theorem, right? The good one. Right. So Jen, put that away for a second and watch this. So here's the other way we can say the work energy theorem. We could say that the work due to non-conservative forces equals the change in total mechanical energy. This is a really cool way to do it. So, but this isn't in the book. This is a little more sophisticated, but I want you to kind of see this. Last thing I want you to see, and then we can move on to other stuff. All right, so remember that mechanical energy is just the sum of kinetic energy and gravitational potential energy, right? So U equals just mgh, right? So if we took the same problem, right? If we took the same problem here, so here's the hill, 11.2, right? Once again, we got the bike at the bottom that's got all kinetic energy, right? It's mechanical energy. If we set H equal to 0 there, which would make sense, and now you can see why it really makes sense, because it makes the mechanical energy easier to deal with. It's all kinetic at the bottom. It'd be all potential at the top, right? So down here, the initial mechanical energy is just initial kinetic energy up here. The final mechanical energy is just the potential energy at the top, mgh, right? Okay, what is this non-conservative business, right? Remember this talk. So a non-conservative force is a force where the path length that you take changes the amount of work that's done, right? So what's our classic example of a conservative force?
Doing it.
Is gravity, right? Is the classic example. Gravity is one where if I pick an object up from here, it doesn't matter where I put it on the shelf, how high it is, or if I take it there in a straight line, or if I do that, it makes no difference. The amount of work I'm doing is the same either way, right? Any extra work I do, if I pick it up too high, I get back from gravity when it comes back down, right? Not the case with friction. Here's the example we did in class. You might remember, if I want to go from here to here, I can push it right there and do some work against friction, or I can push it through a much bigger distance and do a lot more work and end up in the same place, right? Because the whole time I'm pushing it, I'm having to do work, right? So in this system right here, what's the only non-conservative force acting? Friction. It's the only one that's doing work, right? Okay. So the work due to non-conservative forces is really just the work due to friction, right? And that's equal to the change in mechanical energy. Well, that's just final mechanical energy minus initial mechanical energy, right? So then the final mechanical energy is just gravitational potential energy at the top, right? It's lost all its kinetic, it turned it into potential, but it lost some on the way up. So it's mgh minus the initial kinetic or initial mechanical energy is all kinetic. That's 1/2 mv naught squared. That's the work due to friction, right? And if we want to find the ratio of the work due to friction divided by the initial energy, well, that's just kinetic energy, right? We're going to get the same equation, aren't we? Right? We're just going to get the equation mgh minus 1/2 mv naught squared divided by 1/2 mv naught squared, and we can cancel the m's just like before. Now we're right back where we started. We don't have to finish the rest of it because we already did that math, right? But now it's just a calculator problem. But isn't that easier? I think, right? Okay? All right. So that should get you going. So let's, we haven't done this